Hi, my name is Kevin Kam, and I am a member of Team UltraCool for LN6350 VLSI Design course, taught by Professor Peter Kingett. We designed an ultrasound analog front-end receiver in a 65nm process. We were lucky to participate in this course and to be a part of a silicon IC tape-out, from the CAD design all the way to the post-silicon testing. Before we get into the project, we would like to thank the teaching staff for their insights and support, and Apple for generously funding our project. Without all of the people supporting us, this project would not have been possible. This year, we worked to design an analog front-end receiver for ultrasonic signal processing. The left figure is the top-level layout from the Cadence layout viewer, and the right figure is the micrograph of the chip post-fabrication. In the design, the top left corner of the chip features the purely analog front-end receiver, while the bottom right of the chip is an 8-bit SAR ADC. Throughout this video, we will be discussing the system overview, a demonstration of our chip in action, and some discussion of our post-silicon characterization. Before we begin with the silicon design, we should discuss what ultrasound is and why we care about them. Ultrasound signals are acoustic sound waves that are at a higher frequency than human hearing. This is commonly between 20 kHz and up to hundreds of megahertz. Ultrasounds have many applications in sonochemistry and medical imaging. This chip was designed to capture frequencies between 2 kHz and 70 kHz, and to explore applications at lower frequency ultrasound. To get the acoustic signals into the chip, we used a couple of different ultrasonic transducers. The first sensor we used was a Murata 40 kHz transducer that is commonly utilized in acoustic range-finding applications. It generates an output voltage when it senses a 40 kHz sound wave. Secondly, we used a PVDF turfy-based thin film device as a current input sensor, developed in the cited work. These sensors generate different signal outputs in response to physical actuation, and will be the two main inputs to our chip. More specifically, they form the interface between the outside ultrasonic signals and our internal silicon. This is the system-level block diagram of our chip. The signal flows from the left with either the voltage-based sensor or current-based sensor as the input, all the way to the right with an analog differential output, as well as a serial and parallel digital output from the ADC. As our chip is designed to be compatible with both voltage-based and current-based ultrasonic sensors, we implemented a selectable input stage so that the input to the chip could be chosen between either sensor. The voltage-based sensor signal is fed into a low-noise amplifier, or LNA, while the current-based sensor is input into a charge amplifier, or CA. The output of both amplifiers then go to a multiplexer, or a MUX, where the input stage could be selected using a control signal, MUX select. Whichever signal was chosen by the MUX is then passed on to the single-ended to differential converter, or S2D. The S2D transforms the single-ended sensor inputs into differential outputs. After the S2D, the newly differential signals enter the programmable gain amplifier, or PGA. The PGA has 8 separate gain states, ranging from the lowest, 000, to the highest, 111. The gain is programmed with a 3-bit digital bus, G0 to 2, which sets the gain level. The differential output of the PGA is then sent to the GMC filter, which is the final analog stage and outputs a differential analog signal. The filter has a designed cutoff frequency of 70 kHz and features a tunable resistor, I-bias filter, which allows users to make fine adjustments to the cutoff frequency in the presence of heavy process variations. The final part of the system is an 8-bit SAR ADC, which processes the differential analog signals coming from the filter, and outputs an 8-bit digital signal in both parallel form and serial stream of 8-bit data at a rate of 1 MHz. A common application for this chip would be in an ultrasonic rangefinder. How it works is that an ultrasonic signal is generated by a transmitter. This signal travels at the speed of sound until it contacts a detectable object. The sound waves are then reflected off the object and then received by our analog front-end chip. The difference in time can then be used to calculate the total distance as the sound waves travel at a constant rate. Next, Hui, one of my fellow team members, will demonstrate our chip in action. Take it away, Hui.
Hi, I'm Huy, and I'm going to talk about our demo setup. So in this case, we have a transmitting sensor, which is connected to a function generator, and the receiving sensor. And in the scope, we have the blue line, which represents the rising edge of the signal coming out of the transmitting sensor, and the green line, which is the output of our chip. And as we are moving the transmitting sensor away from our receiving sensor, we can see the time delay between the transmitting and the receiving signal increase, and in this case we keep moving out until we reach a distance of 68 centimeters, which will corresponding to a time delay of 2 milliseconds, which also corresponding to 1 time division on the scope right here. In this case, we have a sensor that is 136 centimeters away from the receiving end, and as we can see, the time delay is about 2 division, which is 4 milliseconds. And in this case, we're moving the sensor closer and closer to our receiver from 136 centimeters back to 68 centimeters, and we can see the time delay between the transmitting end and the receiving end is shrinking as we're moving closer. And as we move to 68 centimeters, the time delay is about 2 milliseconds again, which is 1 time division in this case. The scope transient signal from the demo can be seen more clearly here. The transient signal for the distance between the sensor and microphone of 68 centimeters is shown in the left, and for the case of 136 centimeters in the right. The red line represents the rising edge of the transmitting signal, while the blue line represents the output signal from our system. It can be seen that in the left figure, the input sound wave reached the receiver in approximately 2 milliseconds. Assuming the speed of sound is 343 meters per second, the approximate distance is 68 centimeters, which matches the actual distance. In the right figure, the time delay was approximately 4 milliseconds. The time of flight of the distance measured to be approximately 136 centimeters, which matches closely with the theoretical calculated distance using the same relationship. Now we are going to discuss the design of the PCB used to bring up and test our chip. To bring up the full functional system using the chip, we designed a 2-layer PCB using KiCad. Apart from the chip itself, we also included a microcontroller and an LCD display to process and display data, as well as a prototyping area in the bottom left of the board for debugging purpose. In the left, you can find the 3D view of the board rendered by KiCad, and in the right, this is the circuit board after being assembled. More details about the PCB design can be found on our website. Next, my teammate Jason is going to talk about the chip testing and characterization result.
Hi, I'm Zixuan Huang. Now I'm going to introduce the chip testing section. To test the functionality of our chip with the sensor input, we hooked up a Murata MA40S4S 40 kHz ultrasonic transducer to a function generator and used it as a transmitter. At the receiving end, which is the input to our chip, we used the same Murata ultrasonic transducer as the voltage-based sensor input to the system, while using the fabricated piezoelectric sensor as the current-based sensor input. For the test using the voltage-based sensor input, the function generator outputted a 1 volt peak-to-peak signal, 40 kHz sine wave to the ultrasonic transducer. For the test using the current-based sensor input, since the piezoelectric sensor has a low sensitivity to the input ultrasonic signal, we increased the input signal to the transmitter to 8 volt peak-to-peak. In this figure, we can see the transient response of the system using the voltage-based sensor input, with the transmitter distance at 1 meter away from the sensor. The gain setting was set to the max gain to increase the sensitivity. As the transmitter was far away from the sensor, the signal received at the input sensor was very small, as can be seen in the figure. However, as the signal moves through the system, the high gain setting along with the high and low frequency filtering and the differential protection from the common mode noise resulted in a cleaning amplified differential signal seen at the output. We also carried out the AC frequency response of the system with the lowest gain setting of 000 and the highest gain setting of 111 using a network analyzer. The measured and simulated AC response of the case of minimum gain can be seen in the left, which shows a gain of 20.76 dB at the passband and a high cutoff frequency of 73 kHz. Meanwhile, the response of the max gain can be seen in the right, which shows a passband gain of approximately 53 dB and a high cutoff frequency of 73 kHz. As it can be seen, our measured AC response matched well with the simulated result. Okay, now my teammate Yichen will introduce the current-based sensor testing.
Hi, I'm Yichen. Now let's switch to the current sensor input signal paths. The left figure on this slide shows the transient waveform of current sensor input. With the transmitter distance at 10 cm away from the speaker, we set the gain to be 000, which is the minimum gain. The blue waveform is the single-end input, and the red waveform is the amplified and filtered differential output signal. The right figure shows the waveform with a distance of 50 cm. The input has lower amplitude due to the longer distance, and the gain is set to be maximum to receive a low amplitude signal input. Also, with the high gain and the bandpass filtering, we have a clearly seen amplified output signal. This slide shows the charge amp system AC transimpedance output. There are two gain settings, which is the lowest gain state 000 and highest gain state 111. Unlike the voltage sensor, the gain of the charge amp is the output voltage over the input current. The high-pass response in the low-frequency region comes from the coupling high-pass filter. In the band of interest, which is 10 to 70 kHz, the system operates as an integrator, meaning the response decreases linearly at a slope of 20 dB per decade. At higher frequencies, about 70 kHz, the filter output pole further decreases the gain magnitude. Additionally, our chip features an ABSR ADC designed by Team 3. For the purposes of the ADC testing and integration with our analog front end, this ADC was used to process and digitize the ultrasound input signal for our chip. The left figure shows the transient waveform of the ADC output. The digital codes are transformed to analog voltages using an ideal DAC. We inputted a 40 kHz sine wave with a 20 mV peak-to-peak signal from the voltage sensor input. The sampling frequency here was set to be 125 kHz. The figure on the right shows the spectrum of the output signal, where we can find several important parameters. For example, the FSDR is 44.72 dB, and the SNR, which is the difference between input signal power and the noise power, was calculated as 40.41 dB, and the corresponding ENAP was calculated as 6.4. More details on the design and testing of this ADC can be found on the Team 3's website page. In conclusion, we have developed an analog front-end chip for both current and voltage-based ultrasonic sensors. We learned so much over the past year and even through all the late nights. The RCA-LVS errors and long design reviews, we all have grown as circuit designers. Thanks for listening to our presentation. We hope this is the first of many chips for 4 of us. Thank you.